Hey everyone, my name is Omar Aguilar, and this presentation is my strength and conditioning needs analysis for rugby, specifically for the Australian National Rugby League as a performance model. I will outline the physiological, biomechanical, and injury demands on rugby, and I will do a compare a case study athlete to the benchmark data found in the literature. And I will finish by designing smart goals and training plan tailored to this athlete. As we know, rugby is an extremely demanding sport from a physiological standpoint. Players rely heavily on the ATP PC system for explosive actions that include sprints, tackles, and jumps. But they also need a strong anaerobic glycolytic system to handle repeated high intensity bouts through the 80-minute match. At the same time, rugby athletes require a solid aerobic base. Most elite rugby players sit around a 50 to 60 VO2 mass, which supports better recovery between high intensity efforts. Strength and power are huge in rugby. Lower body force production supports sprinting and tackling, while upper body strength is key for collisions and grappling. Finally, conditioning is multifactorial. Athletes need repeated sprint ability, high intensity running capacity, and contact endurance because of the constant physical exchange repeated through the match. Biomechanically, rugby is built around explosive locomotion and controlled collisions. Acceleration is more important than top speed because most sprints are almost always under 20 meters. Change of direction is constant for evasion, tackling, and defensive reactivity. Players also generate a lot of horizontal power, which include pushing in scrums, driving in tackles, and bursting forward from static position. Rugby also requires rotational power for passing and kicking. Forwards deal with a greater collision mechanics, require strong trunk stiffness and high levels of absolute force. In contrast, the position of backs perform more multi-directional movement, which require greater speed and rely more on technical skills such as kicking or lateral movement. Overall, as we know, rugby puts stress across the entire kinetic chain with specific biomechanical roles depending on the position. Rugby injury profile is heavily influenced by the collision nature of the sport. High speed sprinting combined with rapid deceleration makes hamstring strains one of the most common soft tissue injuries. The sport also sees a high rate of ACL sprains, ankle sprains, and patellar tendon issues. Upper body injuries are extremely common due to tackling, especially the AC joints, sprains, and shoulder instability. Cervical issues and rib contusions occur frequently in scrums and rocks. Concussions remain a major concern as well, given the impact nature of the game. Risk factors include fatigue, technical breakdown during tackles, and insufficient eccentric strength. All of things we can proactively address to a strength and conditioning program. On this side, I'm comparing our case study, athlete to benchmark values from Bracer et al. 2020, which looked at elite professional rugby players. Strength wise, the athlete is exactly where he should be. If we see his squat and bench radius, they fall right into the elite range, which is a major positive for collision sport athletes. When we move into jump and power metrics, we see a clear weakness. Elite rugby athletes typically jump around 50 to 55 centimeters on a corner movement jump test, and our athlete is around at a 45. That tells us that we need to target neuromuscular power and rate of force development. In terms of speed, the athlete accelerates well. 1.68 seconds in a 10-meter sprint is competitive. However, the 505 change of duration time is slightly lower than the elite standard, which highlights a need for change of duration efficiency and deceleration strength. Aerobically, his VO2 max is actually appropriate for a forward, so conditioning isn't a priority weakness. So overall, these athlete strengths are absolute strength, acceleration, and work capacity, while the biggest opportunities lie in power development, change of duration performance, and maximum velocity. The assessments we're using, which are corner movement, jump, sprint tense, and 505, are highly valid and reliable, so these results give us confidence in targeting or training interventions. So for the SMART goals, I got SMART goal 1, 2, and 3. For SMART goal 1, I target on improving lower body power. SMART goal 2, improve change of direction. And SMART goal 3, improve max velocity in sprinting. I selected three measurable areas where the athletes show the biggest need. As I mentioned, the first goal is improving counter movement jump height from 45 to 50 centimeters over an 8-week block. This directly targets lower body power and rate of force development, which transfers heavily to acceleration, tackling, and general explosiveness in rugby. The second goal focuses on change of direction ability by bringing the 505 time down to 2.28 seconds. We will improve the athlete's ability to decelerate, recelerate, and react to components. This is huge for position specific performance, especially in defensive scenarios. So the third goal targets maximal velocity, reducing the 40-meter sprint time from 5.2 seconds to 5.10 seconds will help improve open field speed, making the athlete more dangerous when making line breaks or covering space defensively. All of these three goals are specific, measurable, realistic, and they will be aligned with the demands of the specific preparatory period. For program design, I selected two exercises per SMART goal based on the most important adaptations we want. For improving cutter movement jump height, I included trap bar jumps at lighter loads to target high velocity power, and a speed focused bat squat to improve rate of force development. For the change of direction goal, I'm using lateral bounce to improve deceleration capacity and force absorption, paired with a 505 repeats to create direct transfer to the assessment we want to improve. Finally, for max velocity, I chose flying 20s to isolate thought and speed mechanics, and the remaining deadlift to strengthen the hamstring and glutes, which are muscle groups responsible for horizontal force productions and leg swing phase stiffness in sprinting. Overall, the design fits the specific preparatory period because we are narrowing the training focus to the qualities that will have the biggest impact on performance, while still respecting the athlete fatigue levels and training calendar, of course. Before I finish, here are the key sources that support the physiological benchmark, injury patterns, and performance expectation, including the needs analysis. The Bracer et al. 2020 study was especially important because it provided peer-reviewed anthropometric and physiological profiles for elite rugby athlete players, which allowed me to compare the case study athlete with the real professional standards. I also cross-check assessments and training concept with both the NSCA Sports Science Test and the Nestor's SNC Guide to ensure accuracy and proper application. These references helped me validate all of the information presented today and gave me a structure for the SMART goals and training prescription. Thank you for taking your time to watch my presentation and go through this needs analysis with me. Learning more about the rugby demands has given me personally a deeper appreciation for how complex and physical this sport really is. I hope this breakdown helps anyone viewing it and understand how strength and conditioning can truly support performance, resilience, and long-term development with athletes. Thank you very much. If you got any questions and if you'd like to talk about any sports science or athlete development, please feel free to reach out to me anytime. Thank you.